Hello engineering students, this is Mr. O again. I'm going to jump straight into axial or angled loads on a beam. So I'm going to have a look at this particular question where we have a simply supported beam and we have a fixed or pinned support on the far left hand side and a roller support on the far right hand side. And about 0.7 meters from the right hand side we have a load, but it's not a normal load that is perpendicular. It is actually at 60 degrees from the horizontal plane. So the question asks us to calculate the reactions in both the left hand side and the right hand side at the supports. So let me jump straight into it. The first thing I'm going to do is I'm going to redraw this so that I make sure I do not make a mistake. So I have a fixed or pinned load with a beam and a roller support. So I just draw that just to get my clarity. Okay, this is a fixed or pinned support, R left. This is my R right, my reaction on R right. Being a fixed, I know I'm going to probably have a force, well, I will have a force of the left vertical, and I will have a force on my left horizontal. I automatically assume, because I know in my assumptions, if I look at this whole beam is in equilibrium, I'm automatically going to assume all my forces, all my vertical forces up will be positive, all my vertical forces down will be negative, and all my forces to the right will be positive, and all my forces to the left, my horizontal forces to the left will be negative. So straight away, I've also then got, and I assume they're positive, therefore they're looking like they're going upwards. I assume it's positive, so it's going to be to the right. This one is a roller support. It's only going to be in one direction, which is a vertical support. I'm going to assume it's up as well. So you automatically assume that they're up. The calculations will tell you something different if it requires to. So from there to there, it is 0.7. Look, I'm doing this a long way. When you guys do your exams and things, it'll be a lot quicker. And 2.3 meters from the left is this force that is 60 degrees from the horizontal plane, and it has 5 kilonewtons. So we know our units are meters, and we know that the force is kilonewtons. Don't have to do any changes, nothing special. Jump to the assumptions quickly. As I said before, these are my force horizontal and force vertical. Vertical being there and horizontal being there. Because it's in equilibrium, the sum of the forces down will equal the sum of my forces upwards, which then gives me that if I put this over, that goes over to the other side and it becomes force downwards. And the same for my moments. A moment effectively being the turning effect of the force acting on this particular body relative to a point. So my moment will be, for this entire beam, my left hand side moments, my clockwise moments will equal my right hand moments. So the sum of all the moments across this beam should be equal 0, because we haven't been told it's not in equilibrium. And therefore the sum of my moments that are counterclockwise equal the sum of my moments clockwise. You don't have to do all of this in the exam, you just draw a little picture, but I'm doing it to continually remind you of it. They're both positive. I move this to that side there. 0 equals positive sum of my moments clockwise minus sum of my moments counterclockwise, which gives me the clockwise is positive and counterclockwise is negative. So those are my assumptions already. So the next thing, I've drawn it. I have a good idea of where it is. Before I continue, I need to resolve this angle. I'm going to redraw this here. So this is almost like a step 1A, a part of my assumptions. I need to take this angle, this force at that angle, and resolve it to its vertical and horizontal forces. We can only work with the forces if they are vertical or horizontal to that beam. So that force is effectively a resultant of a horizontal force a vertical force and a horizontal force. So this is my hypotenuse, this is my opposite, and this side is my adjacent. And I will probably go through this in another basics of resolving these to the horizontal and vertical forces. But we know from previous work that's been done that my force vertical equals my hypotenuse times sine theta. And the same with my force vertical is going to be the hypotenuse times cos theta. So straight away I can work that out. I know that my height is 5 kilonewtons that way and the angle is 60. So it'll be 5 kilonewtons times sine 60 degrees. And that's my vertical, my horizontal. Obviously, if I'm pushing on a force that way, I'm going to be pushing in that general direction. This is my resultant. So it's going to be down and it's going to be that way because my resultant is pointing this way. You can just see it from the way the picture shows. Also, don't forget, if I am at 45 degrees, a bit of quick bit of theory here. If I'm at 45 degrees to the horizontal, my force vertical will equal my force horizontal. If my angle is greater than 45 degrees, let's just say 60, straight away, just visually, you can see that my force vertical is going to be greater than my force horizontal. You can just see by the length of that. That length is longer than that length. If it is less, let's say 30 degrees, you can see that my force vertical will be less than my force horizontal. My force horizontal will be greater. So keep that in mind for a bit of common sense when you're doing your work. So straight away, when we finish this, I tend to jump around a bit in my calculations. I hope that's okay. And therefore, my force vertical over here is, let me do this. So that is 5 sine 60, 4.33 kilonewtons. And my force horizontal is going to be less than that because it's a steeper angle, and you can see visually it's going to be less. So I'll go 5 cos 60, 2.5. So that actually makes sense. You can see that. So technically, instead of having that, I resolve that to look like this. This being 4.3 kilonewtons and this being 2.5 kilonewtons. And then I just solve for these, which is a right-hand reaction, which also technically is my force of the right vertical, and this would be my force of the left vertical, force of the left horizontal. So step number 2, I keep on saying so, I noticed that. We jump into doing a moment calculation. So I've drawn the diagram, I put down my assumptions, I have then calculated these, I've resolved the angled force to become both a vertical and a horizontal force. My next step is to then do a moment calculation, so sum of the moments calculation, and my third step would be to do a vertical and horizontal calculation to work at the other side. Quickest way, start on the left, let's do moments about RL. So take moments around RL in order to find the side I don't know, which is RR. So from this point, it now acts as I take this beam as if it is pinned there and I almost ignore that force, and it can move like a seesaw pinned over there. I now look for if sum of the moments is 0, and I can work out 0 equals positive, all my clockwise moments. Don't forget to write down my moment is force times distance. So it's force times distance minus force times distance. These are the clockwise moments, and these are the counterclockwise moments. Remember, I'm looking at that. So my clockwise moments are positive. All my counterclockwise moments will be negative. So let's have a look. From this point, what is going to cause, remember I now have resolved that to that and that. What is going to cause this to go clockwise? So that force there. So it's plus. What is my force? It is not 5 at that angle, it is 4.3. 4.33 kilonewtons times how far is it from that point? 2.3. Any other forces now causing it to rotate in a clockwise motion? I don't see any. So if I look then back at this side now negative, I'm going to do all my counterclockwise moments. I don't have any except for that reaction there. The force that I'm supposedly, that roller support is supporting that beam at. So that is going to be force of the left vertical. That's my force pushing upwards, causing the beam to turn into a counterclockwise moment, which is why it's in the negative brackets. And it is 2.3 plus 0.7 is 3 meters from the end. There we go. I have no other forces to look for. So let me work that out. 2.3 times 4.33, 9.959. I'm going to leave it like that so I can get more as accurate as I can be. Minus 3 force left vertical. I'll take that to the other side. 3 force left vertical equals 9.959. Divide that by 3. Force left equals, divided by 3, 3.3196. Don't know how far you want to go. It's up to you. So I know that my force supporting that beam on my right hand, I keep on saying L. I made a mistake, my apologies. So sorry. I don't know why I do that. Force right vertical. My apologies, guys. You're probably wondering, why did I do that? It's positive. Because it's positive, it is pushing upwards. So it is supporting the beam on the right hand side with a force of 3.31. Don't forget the kilonewtons of force upwards. I'm going to now tear this off and continue with the next part. The next part is telling me I've found the side, tick, and I need to find the left and the right. So that is my step 3. Step 3 is, well, it's going to be pretty quick and easy. I'll look at the force horizontal, because the sum of my forces to the left equal the sum of my forces to the right. I'll redraw it on this side again. I'll take this over to this side to prove my assumptions. 0 equals positive sum of the forces to the right minus sum of my forces to the left. You can see that all my forces to the left in my horizontal are negative and my forces to the right are positive. So let's have a look. What forces do I have? I have, at that point, I know there's a force to the right. but I don't know what it is. So I'm going to assume it's positive. Therefore, it's going to be RL horizontal minus the force that I know is now occurring here, which is this one here, minus 2.5 kilonewtons. How easy is that? That goes to the other side. RLH equals positive 2.5 kilonewtons. Doesn't that make sense? Here's my beam. There's other way around. I'm not having a good day today. Over there, it's pushing at 2.5, which technically is negative. It's going to the, and this side will have to, in order for it to balance, it has to be 2.5 to balance it out, positive. I hope that makes sense. And then I work out force vertical, and the same thing. Now I'm going to prove the vertical part. Up is positive, down is negative. And how do I do that? So therefore my sum of all my forces downwards should equal the sum of all my forces upwards. I'll take that over to the other side. So all my forces going upwards, because I've taken this to this side, it becomes a negative. The sum of all my forces downwards. I really just proved that all my downward forces are negative and all my positive forces are upwards. So what do I have so far? I know what that force is. That force is 3.3196 kilonewtons up. That's a positive force. I don't know what this is, which is what I'm trying to solve. That is my force left vertical, and I'm only looking at my vertical forces. This is that force there, 4.33, there should be a dot, kilonewtons. So this is how we solve it. 0 equals all my forces pointing upwards. It is force LV plus 3.3196 minus the only force pointing down is 4.33 kilonewtons. So I'll extract that. Force left vertical plus 3.3196 minus 4.33 kilonewtons. What does that become? So positive 3.3196 minus 4.33 is force LV minus 1.01. If I want to go to the next level, I'll take that to the other side. Force left vertical equals positive, because it's negative, it goes to the other side and becomes a positive 1.01. Basically, I wouldn't go too far. There we go. I can prove that now if I draw a force diagram, which is really .5 kilonewtons positive. This is now that answer there, 1.01 kilonewtons positive. This is 3. No. Yes, it is 3.3. And this is negative 2.5 kilonewtons, and that is 4.33. That plus that. Technically, when you draw this, you don't have to put the signs in, but downward forces will be the same as those two added together, and your horizontal forces will be the same. And that's your answer. And where your answers are normally marked, or your marks are allocated, is finding that it's finding that, it's finding that, that, and that. So this can be anywhere between 3, 4, or 5 marks, depending on the marking allocation or the marking schema of the teacher. I hope that makes sense to you guys. And yep, I'm going to do 2 more examples with angled or axial loads onto a beam, just to give a bit more practice in resolving the angled forces into perpendicular forces or horizontal forces to the beam. And that's kind of how you do it. Hope that helps.